Hi, this is Miss Nickel, and the purpose of this video is to understand three different categories of force. And this is important both just to have a clear understanding of Newton's laws and then to be able to apply those in order to solve problems related to Newton's laws, like the elevator problem. So the three different categories we're going to talk about are weight, normal force, and net force. And we're going to start out with weight. So I'm just going to move these two back to the side again. And weight is a force. And what I want to talk about is the distinction between mass and weight, because weight is actually a force and mass is part of the definition of weight. So mass is just the amount of matter in an object. Whereas weight is a measure of the gravitational force acting on an object. Okay, so weight will vary depending on the gravitational force, but mass will not. Okay, so if we look at the Newton's second law, the equation is force equals mass times acceleration. And so since weight is just a category of force, we can say that weight is equal to mass times the acceleration of gravity. And when I ask you what the units of weight are, because weight is a force, the units will also be newtons. So the way we can prove that to ourselves then is just looking here. Newton, the definition, is actually equal to the units for mass and acceleration put together. So we have the kilogram meter per second squared, and that's what a newton is kilogram meter per second squared. And when we look at weight, we get the same units. So weight, like I said, is going to be in newtons. Mass is part of the definition of weight, so that's going to be equal to kilograms times the acceleration of gravity specifically. So we could put that in. Actually, let's just put that in as 10 to keep it simple. 10 meters per second squared, okay, in the case of an object here on Earth. So we're used to kind of thinking about mass and weight being the same thing because we don't see much difference here on Earth since the acceleration of gravity is pretty constant. And in our everyday life, when we step on a scale, we are actually looking at force. The unit that we use, the pound, is part of the British imperial system, and that is equal to something called a slug. A slug is the unit of mass times 32 feet per second squared, which is the acceleration of gravity in feet per second squared. So that's what a pound actually is. It is also a unit of force, and we don't usually think much about mass because we don't need to. But when we start to apply Newton's laws, we really have to make a distinction between those two things. And just to make that a little bit more clear, I think I can just kind of scroll down on this thing here. I'm going to try that. Yep. Okay. So let's just talk a little bit more about how those two things are different. And moving back to this. Okay. So if I have the classic example that you have probably heard, is we take a chunk of mass, any kind of mass. I'm going to say that's a 1 kilogram mass. And here on Earth, that mass is going to have a weight equal to 10 newtons, right? Because the weight is going to be 1 kilogram times the acceleration of gravity, which is 10 meters per second squared. And so that's going to come out to 10 newtons. Now, if I take that same 1 kilogram mass up to the moon, where the acceleration of gravity is 1.6, about 1.6 meters per second squared. Hope I've got that right. Then I take that same 1 kilogram, right, multiply it by acceleration of gravity on the moon, and I can see now that same mass has a weight of 1.6 newtons. So we can see a big difference then when we change the acceleration of gravity, and that becomes a little more clear. Now, how can we make a distinction for mass then? How do we know how much stuff is in something if we can't figure it out by weighing it? Well, the only way to measure mass is to measure it against a standard. And that is what a laboratory balance is for. So you have all probably used one of these at one time or another. And the way they work is that you put a known mass on one side of the balance. So let's say we have 0.1 kilogram known mass on this side, and that's called a standard. And then on the other side, you're going to have your unknown amount of mass that you're going to be measuring, and you will be sliding back and forth a weight that's on this sliding scale here until the meter in the center shows that the two masses are balanced. And then you will know how much your unknown mass on this side, how much mass is in it. And this on this side was your known, right? Okay, so that's how we do it in the lab, but how do we know what a kilogram is in the first place? Well, somebody decided that a long time ago. So the standard for the kilogram was created from a hunk of platinum iridium metal and has been housed at the International Standard or International Bureau of Weights and Measures in Sèvres, France since 1889. So that standard is known as International Prototype Kilogram, but more affectionately known as Big K. And Big K has many brothers and sisters housed around the world, and we have 7 copies of Big K here in the United States. And that's in the US. And so 7 copies of the 1 kilogram standard. And these are stored at the National Institute of Science and Technology in Gaithersburg, Maryland, which is deep underground. And this is a picture of one of those copies of Big K that's stored at NIST. And so this one is known as K4. Okay, now you can see that K4 is stored under very precisely controlled conditions, and so is the original Big K. But even so, Big K has lost about 50 micrograms of mass since it was created in 1889. So that doesn't seem like very much. It's only the amount of mass in one human eyelash. However, when you consider the fact that these standards are used to calibrate all of our scales all over the world, then this becomes pretty important, right? That we have a kilogram that doesn't change. So scientists have been worried about this, and in 2018 they came together. There was an international conference, and they decided to tie the mass of the kilogram, or to define the mass of the kilogram, using something called the Planck constant, which is a universal constant in nature that relates the amount of energy in a photon to the frequency of electromagnetic radiation. So it's not important that you understand that exactly how that works. The important thing about that is that the Planck constant never changes, and this makes it so that our definition of the kilogram also never changes. Okay, so that was a bit of an aside on mass and how we know the mass of things. If you remember, we were comparing mass and weight, and mass is the amount of stuff in something. Weight is the gravitational force pulling on that stuff. I hope that this has been helpful for you. And now we're going to move on to normal force. In this part of the video, I'm going to talk about something called normal force. And normal force is the perpendicular contact force exerted by a surface on another object. It's a lot easier to understand what normal force is when you actually draw a diagram and see what it looks like in a picture. So I'm going to draw two different diagrams. One is going to be what we call a physical diagram, and that shows the forces occurring between two different objects. And the other one, let me move that up again, is going to be a free body diagram, which we've talked about a little bit in class. And that just shows the forces on one object, a single object. Okay. All right. So with the physical diagram, we draw the forces from the centers of the two different objects in the direction of their interaction. Okay, so we have one force going down here. That's going to be the force of weight. And since that's going downward, to do it really correctly, we have to say that's a negative mg, negative mass times the acceleration of gravity because it's going downwards. And then we have the normal force here, that is that surface, that perpendicular contact force, which is pushing up against the block with an equal amount of force. And we'll say, because there is a surface here, I think I forgot to draw that in, but there is a surface. That's very important. There we go. So that normal force is equal in magnitude and opposite in direction. We're going to give that a plus mg. Okay, so in the other case here, this block is also resting on a surface. Here we go. Wasn't lined up, bothers me. Okay, so I'm going to draw the surface in right away this time, just like that. So we know that it's resting on a surface, right? Okay, so then we're going to have the everything in a free body diagram. So we're only talking about one object. It has to go from the center of mass of that object. So we're going to have the weight acting downward again, and that is still going to be equal to negative mg. But in this case, we're going to show the normal forces acting upward from the center of mass of the object. And you're going to see that a lot, and it's a little bit confusing at first because it's the force of the surface down here push the surface down here at the bottom, but that force, since it's pushing upward on the object, is shown with this green arrow up here at the top. Okay, so you might be wondering why normal force is even a thing, right? Because it's easy to see how weight is a downward force, but a surface is just something solid. So why do we even think of that as being a force? And that's a little easier to understand when we consider the example of a spring. So here I have one of these playground toys. It's a springy thing that my kids used to love when they were little, and you can sit on at the playground. I really like this one that is a shark. So when a person sits on one of these, like this, they're going to cause a downward compression of that spring. Okay, so this is a person, their force is acting downwards, right? A little hard to see there, so they're causing downward compression of the spring, and the force of the spring is acting upwards, right, until the two balance out and the person is not able to compress the spring anymore. So it's pretty easy to see how the spring exerts an upward force on the person, right, through the shark. Okay, so if the person is standing on a surface or any object is resting on a surface, then it's actually pretty similar in that there's still this slight compression, even though for most surfaces, this kind of compression is very slight, right? But there's still a slight compression of the surface, and that is caused by the person's weight going downward towards the surface. And then the surface is exerting this normal force back upward on the person, okay? And that's just like the spring rebounding. Okay, so far we've only talked about objects that are resting on a horizontal surface. So the last thing that I want to go through is just what a normal force looks like when you have an object that is resting on an incline, which is a tilted surface, right? So you have to remember the definition of the normal force is it's that force perpendicular to the surface of contact between two objects, okay? So you have to look at what um, the surface of contact is here, right? So our surface of contact is this inclined plane. And so the normal force is going to be perpendicular to that, and that's shown right here. It would go like that, perpendicular to the plane, but not to the ground. Now, the force of gravity is still going to act straight down and always acts towards the center of the earth, right? So that shows your force of gravity here. And that force can then be divided into its components. So it's going to have a component that is perpendicular to the surface and also a component that's horizontal to the surface like that. And interestingly, then these different force vectors form an angle here, theta, which is equal to the angle of the incline. So then you can do some trigonometry, and depending on which different parts of this you know, if you know the angle of the incline, or if you don't know that, but you know the weight of the object, and one of the other force vectors, then you would be able to solve for the angle of the incline. So that could be something interesting to try sometime. Anyway, that's a little bit of an extension for what you guys need to be doing right now. And basic thing is just understanding that the normal force is that perpendicular contact force, which is equal in magnitude and opposite in direction to the downward force of the object. And we'll just be talking about objects with horizontal surfaces for now. Okay, so now we're going to move on to net force in the next part of the video. Okay, so in the last part of the video, we're going to talk about net force, which is probably our most important related force concept for Newton's laws, and is really based on understanding weight and normal force. So that's why we talked about those first, and also understanding what vectors are, which we've had a lot of with acceleration and velocity. So net force is the vector sum of all the forces acting on an object. So we know velocity and acceleration are vector quantities, and so is force. That means it has magnitude, like a scalar quantity, right? That's the amount, but it also has direction. And direction is really important. We can't forget about that because that's going to determine whether the forces add together or cancel out. So to take a closer look at net force, we're going to go through our example of the free body diagram here, the block that's resting on a horizontal surface, and draw in the forces on that first, just like we did in the previous video. Okay, so first we're going to talk about our weight. So our forces are going to go from the center of mass. Weight will be acting downward, and weight is equal to negative mg, mass times the acceleration of gravity. And we're going to say that we have a force of negative 5 newtons then. Newtons is our unit of force, and that's acting downward. So we'll also draw in the normal force, which is the force that's perpendicular to the contact surface between two objects. And so that force is going to be going up in the opposite direction. That surface is pushing back with an equal amount of force. So that's going to be plus mg, and that's equal to plus 5 newtons. And you can see that even though this object is stationary, it's not moving, right? There are forces acting on it, okay? So we'll never say that a stationary object has no force acting on it. There are always forces acting on it. And so the question is then whether or not the forces cancel out. And the way that we describe that is by looking at net force. We can represent net force mathematically using capital letter F with the word net in subscript, and then Y or X to indicate whether we're talking about forces in the X or Y axis. And another way to write that, it's also equal to summation of forces in the X or Y direction. So we can use this Greek letter sigma and then write capital letter F after that. Summation of forces, again, with a Y here, subscript Y, indicating what direction we're talking about. So a lot of explanation for that, but basically, when the object is stationary, and we're talking about the Y direction here, the forces are canceling out. So we have an F net, or summation of forces, in the Y direction that is 0. And we could write that out a little bit more, just like this. We can set summation of forces in the Y direction here equal to plus 5 newtons, which is the normal force, plus minus 5 newtons, which is the weight, which would be the same as minus 5 newtons, and that is equal to 0 again. So this means that we have no net force acting on the object, which is the same as saying there is no unbalanced force. And when we have no unbalanced force, that means we will have no acceleration. And that is the key idea with net force, that you do not get acceleration unless there is net force. And net force is the summation of the vector forces acting on the object. Okay, so now let's move on to some of the problems from the test where we have forces acting on objects in both the X and Y directions. Problem number 16 on Newton's laws test part 1 asked us to give the direction and magnitude of net force for 4 different free body diagrams. So I'm going to go through 3 or 4 of those now and apply what we've been learning about weight, normal force, and net force. So in situation A, I'll go ahead and draw in the forces from the test. So it told us that we have the force of gravity acting downward with a force of 3 newtons. So that tells us that the block has a weight equal to 3 newtons. So that's negative mg, which would be equal to negative 3 newtons. So that isn't written in the problem, but anytime we see force acting downward in one of these free body diagrams, we're going to assume that it's negative unless we are told otherwise. Okay, then it shows us the force acting upwards, F normal. So that's our normal force going upward, and that is going to be equal and opposite in this case. Now, we'll learn when we get to the elevator problem that normal force does not always have to be equal. I'm sorry, that was a plus. Does not always have to be equal to weight. And in that case, it can either add to what's something called apparent weight or subtract from apparent weight. In this case, though, the normal force is equal to the weight. So those are going to cancel once again. But we also have forces in the horizontal direction. So we have a push force, we'll call it, being applied this way. So I'm going to call that F push, and that is going to be equal to 5 newtons. And then we'll say that the force going in the opposite direction then is going to be our pull force. In this case, that is also equal to 5 newtons. But we'll say that that is negative 5 newtons. So a force that goes to the left, just like a force that goes down, is going to be negative. So we'll call that negative 5 newtons. So then if we go in here and we sum these forces, we can sum them in the 2 different axes. So we have summation of forces in the Y direction, and that is going to be equal to, not that it matters, but I was going to do that in black, And let me move up my page a little bit here. Okay, so summation of forces in the y direction then is going to be equal to, we'll start with weight. No, I think last time we started with normal force, right? Yeah, so we'll start with normal force. Doesn't matter. So that's positive 3 newtons minus or plus negative 3 newtons, but we'll just call it minus 3 newtons. And that's going to be equal to 0. So we have 0 net force in the y direction. And then we can also look at summation of forces in the x direction. So if we look at our summation of forces in the x direction, that over here, and so we can set that equal to the push force, which is a positive 5 newtons, minus the pull force, which is negative 5 newtons, so that it comes out to 0. And so since both the summation forces in y and x are 0, then we can say that F net for this object is equal to 0. And since the object wasn't moving in the first place, that means that the object is stationary. It has no acceleration. It is not changing its motion. Now we can look at situation B. And in situation B, once again, we have a weight of 3 newtons. So I'm going to say that weight is equal to negative 3 newtons downward. And we have our normal force, which is equal to that in this example. So we're going to say 3 newtons upward, positive 3 newtons. And so in this case, then our summation of forces in the y direction is going to be exactly the same as it was in the previous diagram. But almost forgot to mention, we have another force in this situation. So that force, we're going to have a leftward pull force here. Supposed to be a straight line, one like that, to the left, and that is going to be a negative 5 newtons because anything going to the left is negative and to the right is positive. So we're going to say that summation of forces in the x direction then is going to be equal to just that negative 5 newtons and nothing else because we don't have any other forces. So now we do have an unbalanced force because our summation of forces in the x direction is negative 5 newtons. So our F net is going to be equal to negative 5 newtons, and we could also say 5 newtons to the left, or be redundant and just say negative 5 newtons to the left. Means that the object would be accelerating to the left. Okay, so let's look at the two other situations on the test. To do that, we need to move down here a little bit. Okay, so now we're going to look at a diagram where our normal force is going to be a little bit different, or we'll start out with our weight. So our weight in this case is going to be 20 newtons. So weight is negative 20 newtons. We always say down is negative. And again, we have an equal and opposite normal force of 20 newtons upward. We have no other forces acting in this diagram. So our summation of forces in the y direction then is going to be equal to those two forces, equal to the 20 newtons, positive 20 newtons upward, minus the 20 newtons downward, and equal to 0. No forces in the x direction. So in this case, our F net will again be 0. And our object is stationary. Okay, so now moving on to our last example. And so in our last example, we've got a weight going down that is 25 newtons. So I'll draw that in. We're going to say negative 25 newtons. So that means that is the weight. The force of gravity on this object is negative 25 newtons, but our normal force is not equal in magnitude. So we have a normal force going up that is greater. So that is going to be 40 newtons, and that can happen, we're going to talk about how that can happen in the elevator problem. But if the object is accelerating upward, then the floor will sort of push up against the object, creating a greater normal force so that you can actually have a normal force that is greater than the object's actual weight. Okay, so what do we do here? We go ahead and look at the summation of our forces in the y direction because there were no x direction forces on this object. So we'll go over here, we take summation of our forces in the y direction, and we're going to set that equal to our normal force, which is 40 newtons, minus the 25 newtons. So that's going to be equal to 15 newtons. And that means that our net force, in this case, F net, is going to be equal to positive 15 newtons, which means that the object is moving up. So we're going to say accelerating up, put that right here. Okay, so those are 4 different situations where we calculated net force on an object. So basically, you just have to sum the force in the y direction, sum the force in the x direction, and if you did have a net force going in both directions, then you would have to find a resultant vector to figure out what that net force was. It wouldn't necessarily be in the x or y direction, but it would be at an angle. In this case, we're not having to worry about that, so we're just looking at pretty simple examples right here, and hopefully that clears up the idea of what net force is for you. The next video you should look at is the video on the elevator problem. We're going to talk about the relationship between normal force, acceleration of the elevator, and apparent weight, which is what you have to understand for the elevator problem. Okay, see you in class.